Okay, sir.
Yeah. Once again, I welcome all of you, all my viewers, to this Professor G's Environmental Engineering Tutorials and Publishing channel. Today, we actually earlier, till my earlier videos, last few lecture sessions, we discussed the theory and principles, including the chemistry of coagulation and flocculation, and then also we sort of discussed the design features of rapid mixing unit. And today we will try to understand the use of or applications of these design criteria, parameters and considerations by illustration with a problem also. So this is the design problem on rapid mixing unit, or in short RMU, and this problem I have taken from CPHEEO Manual, because so that if any confusion is there or so, you can sort of consult with the CPHEEO Manual in the appendix part. There are several appendices at the end of this CPHEEO Manual on water supply and treatment. So I have taken this one so that everybody can have access to this, because it is as I have told that freely downloadable also. So that is why I prefer to see, and later on if there is any question also, then for advanced this one course, particularly for keeping in view the competitions or competitive test also, that we may discuss some other problems too, different kind of problems. So through this problem, typical problem taken from the CPHEEO Manual, where the problem statement is given, the design a mechanical RMU, means rapid mixing unit, that using the following data. Now here the design flow is given, detention period. Earlier in my last video, in fact I discussed that these are the ranges which already I have discussed in my previous sort of lecture. And here actually in this particular problem, it is directly given the value, right? All these values, this is the diameter of impeller as I explained earlier, and this is the diameter of the tank. So the ratio is given. This is the rotating or rotational speed of the impeller, also shaft of the impeller, that is this more than 100 rpm. It is recommended that, and G is equal to, that is the mean temporal velocity gradient, that is given here, this 600 second inverse. And for propeller, as I told you earlier, that this may range from, recommended range is from 700 to 1000 second inverse also. Minimum temperature of water, as I have told earlier also in my last this lecture session, that this actually the minimum temperature will give the maximum viscosity or maximum density also. So that is why we will take the minimum based on the, say, last few years this statistical data with regard to temperature. We are using the minimum temperature also, so that we can get maximum viscosity or the density also. Now this, before coming into this, let me just quickly touch upon that the rapid mixing, because we rapid mixing through this hydraulic means also, that is the hydraulic mixing. And this, because as I told you that these are broadly classified, that hydraulic mixing, and another is that mechanical mixing also. Pneumatic mixing that we don't use in conventional water treatment plant also. Now here, as you see here, those who have studied the basic hydraulics also, you must be knowing that the jump, hydraulic jump. So this is the hydraulic jump, this is the hydraulic jump created by adjusting the geometry of that. Normally the bed geometry, so that actually is constructed such that this is actually, this forms the hydraulic jump also. So here from supercritical velocity here, as you see, this is the backwater curves, supercritical velocity, and when it meets, you know, that means the subcritical velocity having depth more than critical depth. Here the depth is less than critical depth, so that is why supercritical. More than this critical depth, that is actually the depth will be more and velocity will be less. Here velocity will be more than critical velocity. So when this actually the water level meets that the critical the subcritical flow also, there will be a hydraulic jump also because of the energy dissipation, because the energy with which actually that water column is coming here, total energy. Right, I am not explaining all this because these are the basic hydraulics, and the hydraulic jump is included in the basic hydraulics. So when the total energy here, this is actually dissipated also in that way, right? So there will be hydraulic jump, creating a sort of, I mean, you know, motion of, I mean, water here. That means stirring and you know, that the turbulence of this water. So that turbulence we use in hydraulic mixing, that by coagulant doser, or so dosing device is somewhere else, say from there the pipe, through pipe it is connected, and the coagulant is dosed here right at the little before the jump, hydraulic jump also. This is one way to sort of, I mean, effect the hydraulic mixing. And here another, as you see here, so this is the, you know, that, I mean, I should say that this is the, say here, if I can draw here, you can understand this. Suppose this is the V, it is open like that, right? So this is cut like that, suppose. So the water will go there, and this actually, when will pass through that, this will pass through the, or over the V notch, or the 90-degree notch also, as drawn here. So this part will be cut out, right? This will be cut. It will be, you know, fabricated in such a way that there is sort of a there is a construction, or there is a you know, that, I mean, there exists a V notch, you know, the V notch. So that actually is, I mean, fabricated by the sort of manufacturer or the fabricator also, and water is coming from there. So when it falls down over a sort of, I mean, channel or so, open channel, so that actually just below the jump where it falls down, there will be turbulence, and we can use that way also the turbulence, and following that actually here this will be the turbulence. And when the dosing is done here, right, the dosing, the coagulant dosing will be, coagulant dosing, that would be here, and then the same, this one, you know, I mean, unit also, it is integrated with a flocculation kind of unit, like this kind of channel, open channel, where the zigzag manner actually, this would be there. That means say one wall is like that, right, another is like that, so that the water after coagulation also, it will pass through so many baffles, series of baffles, right, which are, you know, I mean, which are fixed, or which are actually fitted with the channel, inside the channel. So that flocculation is effected also. So these are the hydraulic jump. There are other examples also, like impingement of plate also from different orifice also in the pipe. So that by heating that one or striking that the plate, so there also, I mean, turbulence can be created. So these are all you know, options for hydraulic this one, but as I have told that nowadays, I mean, it's mostly, you know, I mean, mechanical this mixer also, mixing unit also, excepting some sort of rural area or peri-urban, semi-urban area where, I mean, the mixing assembly is difficult to get repaired easily also. So there it is better to depend on the hydraulic this one, not to, rather it is better not to depend on the too much on the you know, that, I mean, the mechanical system also, right? So that is why this is there. Now here, so I am erasing this one. This is the hydraulic mixing devices also. So that you will find in any textbooks or CPHEEO manuals also you will get, and there are various other books also, right, where you can get this one. These books names I already I have given, right. I can give it, this is, there are different books, you know, that means let me just give that one. Yeah, IS flocculation, I think I have already told this, that this is IS 7208. This is the flocculation for flocculation, but rapid mixing unit already I have told, right. So this actually, you see that to solve the problem, I am not going beyond that in respect of this, I mean, hydraulic mixing also. You can find it in other, many textbooks are available, Indian as well as, I mean, foreign textbooks are available. So I am not discussing, because this is not very common, you know. So these are given actually. Now what is to be done, last time as I have discussed already, right. So this actually, I am erasing this one because the problem statement you are getting it on board, so you can refer back, right. So now solution. This is a very, you know, short kind of design problems. It is not very, you know, elaborated design, because in undergraduate level it is not sort of, I mean, within your, you know, I mean, curriculum or so. So this is beyond the scope. So that is why I am keeping this to sort of rapid design of rapid mixing unit in a sort of, I mean, short form also. So that actually short length, you can say, too many elaborations also, that will make that things complicated at this stage. So first we will step one, the determination of the dimension of the tank, right. So as I earlier told, determination of dimensions of the rapid mixing tank, right. So the volume, as I have told, of course this is the wet volume or liquid volume, right. Also it is termed as wet volume also. So this is, as I have told earlier, the flow, that is of course the design flow into detention period or time. So that is 250 meter cube per hour into 30 second is given. So 30 divided by 3600, that would be this is 30 second, so this is hour, right. So ultimately this will be in hour. So that will be, say, according to the calculation given in the CPHEEO manual, that is this much meter cube. Okay. Now diameter of the tank, that is circular. Let us, so we have, they have, or rather in CPHEEO manual they have chosen a circular. You could have chosen you know, that square also, right, and same kind of similar method, similar or same, you can say, approach. So that I have already discussed in my last lecture session. So diameter D is that, you know, that this is say D, diameter of the tank, D. I'm just dividing a line so that it gets separated from that. Okay, so pi by 4, pi d square by 4, and given that ratio, that is given 1.5, that ratio of tank height to diameter, that is 1.5:1. So this will be 1.5 D. So that will be equal to volume. So from that you can get D is equal to 1.20 meter, and height or depth, here it is better to take the depth, right? So we are writing here H, the height, or the rather more correctly the depth. That means if this be the tank, rapid mixing tank or so that, as I have told earlier also, I have explained. So this is the freeboard, and that is the liquid depth also, that is the depth. So here as depth, if we write D, so this D will conflict also, so that is why we are writing H also, right? Depth is equal to H, and you can, here you can write H overall also. This is the H of the tank also, it is the overall height also. That way you can differentiate. So H will be 1.5 times 1.2, so this would be 1.80 meter. Now the total depth of tank, including freeboard of the tank, using 1.8 meter plus, let us say, 0.2 meter freeboard. Usually this is freeboard is equal to 0.2 to 0.5 meter, depending on the requirements, right? So we are because unnecessarily larger value will make the tank height more, which will be uneconomical also, and at the same time if it is too short, right, in that case there is a chance when the splashing will be there, when it will be, there will be splashing also, then it may overflow also, go beyond or go over the tank, it may leave. So that is why the optimum is this. So this would be, say, 2 meter or so, right? So you know that the dimensioning is over here, right? So this is having the diameter 1.2, depth is equal to, that is 1.80 meter, and overall that is equal to 2 meter. So that is the dimension of the circular tank. Okay. Now next we will discuss, or next step will be, that will be, I am keeping this one for a sort of short while, so that we can refer back when it is required. So second step is that the computation of power requirement, right? So power to be spent to create the G. Remember, here we are writing that power to be inputted also to create the G value as given. Here the G value is given 600 second inverse. So that degree of mixing, to have that to effect in the tank, we are sort of writing the power to be spent, that is the P. Already this mu V G square, already I have explained this with the notations also, and dimension analysis also we have done. And at 20 degrees centigrade temperature, so that will be 1.0087 into 10 to the power minus 3 Newton second per meter square. That is the mu value, into volume is 2.083 meter cube. And remember here, as I have earlier also stated, that this volume is not the total including the freeboard. This is only that volume, that is the liquid volume, right? So already calculated in the previous step or so. So this is the volume, and this G is 600 second inverse. So second inverse square. Okay, just let me attend. Sorry. So this actually 600 second inverse or so. So here this becomes 756 watts, right? So power per, if you want to check power per unit volume of the tank, the wet volume also, liquid volume. So this would be 756 watt divided by 2.083 meter cube. So this would be 3, say approximately, rounding of this watt per meter cube, right? Which is, between 1 to sort of this is 363 watt, and so this would be, okay, this is the unit volume, and also you can write 750 watt per 250 per unit flow. This will be between 1 to 3 watt per meter cube per hour. So that is just to sort of, and refer back to the earlier, this one's previous different design criteria I discussed. So there from there you can check this values. Okay, and also this is the importance or significance of these values I have discussed, that why it should not be very low, why it should not be very high or so. So that part already discussed, and you see that this is the roughly 3.02 it is coming, and 1 to 3 this is that one. So more or less it is not exceeding very much. So it is very close to the upper limit also, right? Now next, this one, let me erase this one. Okay, so third step, we will now proceed to the third step. Third step, determination or determine dimension of flat blades. If we use the flat blades, it is not like that in that case, flat blades, right? So it would be impeller or turbine type also. So this would be this kind of this, right? So flat blades and impeller. This entire assembly is called impeller also. So flat blade type impeller, diameter of impeller, right? So this would be 0.4 times the diameter of the tank. So 0.4 times already taken in the or given or mentioned in the problem statement also. You may sort of refer back to get this value, the given values. So this would be 0.48 meter diameter of impeller. So this is the diameter, right? So this is the impeller diameter. This is the DI, while the tank diameter, this is DT. Okay. Now velocity of the tip of the impeller, velocity of the tip of impeller. This is also called the tangential or peripheral or tip velocity, same, right? So when it is sort of revolving around this one, suppose this is a shaft or so, right, and this is rotating like that, okay. Now here this is the diameter, and with respect to this this one, this will be the edge of that will be termed as the radius. So in case of radius, 2I pi r omega will be the tip velocity. If you take the diameter, that would be pi d omega or so. In this case actually d means di, impeller, okay. So this actually the tip velocity also, that is equal to, as already explained, twice pi, if we take it say r, smaller, right, lowercase r, omega, that is this rotational speed or the velocity of the shaft, that is omega, okay. And this is r, this is r, this is d, so r is equal to di by 2, okay. So this is this, and here if you calculate this, then 3, this would be twice pi, r is 0.48 by 2 because d is 0.48 taken from here, divided by 2, that gives radius, and this is the 120 rpm, and this will always be expressed, remember that this has to be expressed in rps, revolution per second, and here it is revolution per minute is given. If you see that the problem statement, it is already stated the shaft speed is 120 rpm because this should be in any case more than 100 or so. So this would be this. So divided by 60 to get this or convert this into RPS, revolution per second. So this actually will be 3.02 meter per second, because this is in meter, this is in revolution per second, so this is second per minute, right? So ultimately this will be second here and there meter, so that would be meter per second, which is more than 3 meter per second. So hence okay, it is just exceeding that value. It should be minimum should be 3 meter per second. It is little more than that, right? Next is that fourth step, that is determine the area of blades AP of impeller. So we know that this equation I have written because we are going to use this equation to find out that area of this plate, total area of the plate. This is the area of the blades, or area of the plate or blade, whatever way you say, that is one. Because you see that what is the significance of that? Suppose this blade is rotating, right? This is rotating like that, right? So if AP is more, right, is it's a bit, say, I mean this is rotating, say, instead of that this is rotating, right? So naturally its dimension is more, so more turbulence will be, or power will be required to be inputted also, right? And power already calculated, so to impart that power and to have the obtain that the suitable resistance from this one, the AP should be such that this much power is already calculated, this power, so that is to be inputted also. So this is the power spent, that is P. So half CD is the newtons, CD is the newtons coefficient of drag, and for flat this bladed plates also, or impeller, this should be 1.8. so you can get this value from the literature also, standard literature. VR is the relative velocity of paddles with respect to water. Now when there is no water, say, let me just quickly explain this one. When there is no water, right, then this tip velocity is twice pi r this omega. That is the velocity of tip when no water is there. But when water is there, this will be, the water will put a resistance to the movement of the blades also. So that is why the relative velocity of the this blades also with respect to water will be reduced also to that extent, that is 70 to 80% of the plate, this one. This actually velocity is the edge velocity, as I have already explained. Okay, that is this way it is rotating. So the tip velocity or tangential velocity will be this when no water is there. When water will be there, relative velocity will be reduced also to that extent also. And if we take that CD value here, it is taken 1.8 or so. And if we take that VR is equal to 75% or so. So this actually 75% of V velocity of tip, say this is velocity of peripheral or tangential velocity also. Let us say here we have written VR here, the relative velocity. Here the tip velocity, say T or V peripheral velocity or tangential velocity also. So that actually with reference to that, so 756 already the power calculated. Okay, then half CD this one 1000 into AP, right? And this is 1000 is that, I mean the row. Okay, so this would be AP, which we are required to calculate the blade area, total blade area, and then this is 0.75 times the peak, this tip velocity, that is how much we have got this. So 3.02 cube. Okay, so I am erasing this one so that to avoid confusion also. Okay, this already we have explained. So this would be this. So this is VR, this is rho value in SI system. 1.8 is the compatible, this in compatible unit, the CD value also. So this would be that AP is 0.72 meter square. That means the total blade area, if you put say 4, then the total blade area of the 4 such type of this blades also fitted to the impeller also, which is, this is termed as this assembly, mixing assembly is the impeller assembly, that is actually the turbine type, as I have already explained. So here actually 2 blades is shown, but it may be 4 or 6, as I have already explained. So total blade is there. Now provide, let me write here, better to erase this one, right? So provide 6 blades of size 0.1 into 0.12. This is this much meter by meter. Say this is meter by meter. If you ask me that why 6, why not more or so, then we have taken here, or CPHEEO manual rather, they have taken a very standard, available the blade dimension of 0.1 meter by 0.12 meter. That means 0.1 this side and 0.12 meter on the vertical side also. So that actually will give you that. This is the provide 6 blades. No, this is the just to 6 blade of size at this much. So that is the blade dimension and number 6. Earlier that I have already this one, this is like that, and 6 means here. So when it will rotate actually, this will be you will see like that, right? So this would be, so all will have this one. I have shown already, so I am not extending my discussion here, right? So this is a blades configuration also, and provide 4 numbers of baffles, as I have told earlier, just to sort of minimize the vortex formation and local mixing around the blades also. We need to provide some vertical baffle also. As you see here in the room, so here actually the projected intruded the baffles also, so that when it is rotating like that here, when it is facing this, then the churning will be reaching throughout the tank also. Otherwise it will be, the churning will be around the that impeller only, tip or the blades also. Okay, 4 of the baffles of length, this is 1.9 meter, and projecting, you see that 1.8, so baffles are up to this extra 1.1 meters, so 1.9 meter vertically like that. Just 0.1 meter that has not been covered also, because it is the liquid above liquid level. So this is the sort of pillar like the intrusion or extrusion, you can say, that projection also. And projecting say meter, that means this is 1/10 to 1/12 of the tank diameter also. From that consideration it is taken from the wall, inner wall, of course, inner wall of the tank. That is here, this side also this would be there, and on the other, this one, this diametrically opposite, so that would be, it is like that. I have not drawn just below that, then that would have been more clear. So here in a separate this one figure or the diagram sketch of the plan. So here that mixer, that is 6, that is there, that is the one we are seeing the plan. So here the 4 baffles are provided. So here this is the intrusion 0.1 meter, and the height of that is this. Okay, so to reduce the vortex formation, and now we have to give that, that inlet and outlet pipe, provide inlet and outlet pipes of 200 millimeter diameter. That means if we see now, if we look that tank, this one, so suppose from here it is entering, or it may enter from there also, right? And here suppose the outlet, this is the water level in the tank, this is the inlet pipe of 200 millimeter, outlet pipe, that is the diameter also, that is 200 millimeter, because these are the standard diameter, and you may have to calculate also, but here as per CPHEEO manual it is directly given, because it is very common pipe diameter also. That is why we are using that 200 meters. Otherwise, what should be the velocity in the outlet, what should be the velocity of the inlet, from that considerations you have to find out the diameter of the pipe also. But here straightway we have taken this one here, and there is a sort of churning this here, right? So when that water will go this way, it will move, and this is connected to a driver which actually drives the motor taking the power from the main line, right? So this is the main line, say. So from there, like that one, or I mean any sort of main line is there. From there, suppose this is the main line coming. So it is connected to that drive also, driver, or you can say better drive, right? So that drive, that is, the power is supplied from the line, this one, the electric line. So there actually, and it rotates like that. So with this, let us conclude for today, and next time we will discuss the flocculation, its design criteria, considerations, and parameters, along with the problem. So in my next this lecture session or sessions, it may be, there may be more than one session or so. So in that case, we will discuss this one. So till then, hope that you have understood this, and till then, very good wishes to all of you. Thank you so much.